Okay, now let's discuss the architecture of version 2 and version 3. Here I'm not discussing the results, but you can see the paper to get the results. So this is the figure for TP version 2, this is the figure for TP version 3. So here is a comparison of on some parameters, and for other parameters you can see the paper. So clock rate was 700 megahertz here. Here it is 940. TDP is here just 75 watts. Here it is 280 watts. Here it is 450 watts. So here the power consumption is just too much. So that's why it is liquid cooled. Okay, TP version 3 is liquid cooled. Peak performance here it is. Oh, actually just a minute. Here, so here it is 92 teraflops peak. Here it is 46. Here it is for 16 bit is 123, and for 32 bit is just 4 teraflops. Now here I see memory bandwidth increased a lot from 34 here increased to 700 here and 940 here. As for the off-chip memory, here it is only 8 gigabyte, here it is 16 and 32. So there's a huge improvement. Now MXU is just the matrix multiply unit, so I will come back to it a little later. At least these are the overall outside visible parameters. So let us discuss the features common to version 2 and version 3. So TP version 1 used int 8, whereas version 2 and 3 they provide support for BF16, or that's also called brain floating point 16. Hence they were useful for both training and inference. Whereas version 1 was useful only for inference. You cannot do training on TP version 1. BFloat 16 has same dynamic range on number line, same infinity non-behavior as FP32. So last week I also discussed this floating point number system, which is extremely important if you want to do any deep learning. So I hope you remember that. BF16 multipliers are built out of full adders. So that's why multiplier area and energy are proportional to the square of Mantis bits. In FP32, you have 23 plus 1, that means 24 bits. So you need 576 full adders. Here you need only 121 in FP16. Here you need only 64 full adders. It is this is 8 times more efficient than this. Okay. Memory type and best size. So TP version 1 has DDR3 memory, whereas version 2 and 3 use in-package HBM, which has 20 times bandwidth of TP version 1. This keeps TPU cores well utilized. This is very important. You have to keep the cores well utilized, because anyway there is no mechanism to hide the latency like caches or multi-threading. And they use large batch size because they are specially designed for training. So goal is to use high batch size to achieve high throughput. Okay, now TP version 1 has one tensor core. So this tensor core is different from Google. So from NVIDIA's tensor cores, here everybody uses the same term tensor because tensor is a famous term. So we'll just call it core. Version 1 had only one core per chip, whereas version 2, 3 have 2 cores per chip. Training uses multiple processes. So now you know, right? In CPUs, we have increased the number of cores. In GPU has a lot of cores. So why not increase the number of cores here? That is the reason. Training uses multiple processors, so use of 2 cores per chip is easier to program than having multiple cores per chip. The more number of cores you keep, software becomes a challenge. Utilizing those cores becomes a challenge. Global wires on a chip don't scale with shrinking feature size, so their relative delay increases. Having 2 smaller cores per chip prevents this latency of a single large full chip core. So having one core per chip is also bad. Having too many cores per chip is also bad. An intermediate solution is just have 2 cores per chip. Okay, so neither you have a single core which is very large, which is very slow, and neither you have too many cores that interconnection or communication between them becomes a bottleneck. Now we'll see the specific features of TPU version 2. This is a floor plan of TPU version 2, which has 2 cores. So this is 1 core, and this is 1 core. Okay. Now One core has one MXU, so this matrix multiply unit is called MXU. This core also has one MXU. TP version has large 2D systolic array called MXU to perform matrix multiplication. Version 1 had 256 cross 256 systolic array, which is not fully utilized for sparse DNAs or small size DNAs. To alleviate this limitation, TP version 2 reduces size of systolic array to just 128 cross 128 and doubles the number of MXU. So that's why they have each MXU is smaller, but they have two of them. Total number of max is reduced from 64K in TP version 1 to 32K in TP version 2. Although using further, I mean, instead of, see, they came from 256 to 128, they could have further come down to just 64. That could have improved utilization, but area overhead will become too high. So this is the figure of chips, which has two cores. This is one core, this is another core. Now here, this is only one MXU per core, one MXU per core. Here it has two cores, and every core has two MXU. And this was the figure of a chip. This is the figure of each core. So version 2 has only one MXU. Version 3 has two MXUs. And this was the comparison between this is the version 1 and version 2. Here we have this as the main computation data path. And here we have matrix multiply unit going to the vector unit and then the vector memory, which is backed up in the HBM DRAM. Let us understand this. So training uses undivided on-chip memory, unlike split SRAM buffers used in TP version 1. So in TP version 1, we had accumulators and we had that unified buffer that was split. But here it is combined. It is called vector memory. Merges activation storage and accumulators into a single vector memory. TP version 2 uses a more programmable vector unit, which replaces fixed function data path of activation pipeline of TP version 1. So here it is programmable, and previously it was fixed function. MXU is attached to vector unit as a matrix coprocessor. Now DRAM backs this vector memory. So this is the DRAM is backing this vector memory. So this forms like a compiler controlled memory. Again, it is not a hardware managed. It is again software managed. So TPU fetches 322-bit VLIW instructions from a local memory rather than host CPU supplying them. So training needs large scale. You have to scale training. A custom chip-to-chip interconnect fabric is added. It's not Ethernet connection, it is chip-to-chip interconnect. This enables TP version 2 supercomputers to scale up to 256 chips using this chip-to-chip interconnect. That's what we showed in the beginning. Here, this is okay. Here, that chip-to-chip is not clearly shown, but I think I had another figure where chip-to-chip integration is shown. I'm not sure whether this is. I have to again confirm. Okay, now let us see the specific features of TP version 3. So TP version 3 is a mild redesign of TP version 2 in same technology. It has twice the number of MXUs and twice the HBM capacity. It requires liquid cooling because it has very high power consumption. Here clock rate is increased, memory bandwidth is increased, ISA bandwidth is increased. And this supercomputer can scale up to 1024 chips. This one was scaling only till 256 chips. Here it can scale to 1024 chips. And here are the comparison of features. This is comparison to the Volta GPU, which is of the same time frame. So the memory bandwidth here is also very, very high. Here is also very, very high. The peak performance here it is 125. Here it is 123. So you can see this is highly comparable. TDP is also very easily comparable. Die size, it is much smaller. This is much larger. Clock rate is smaller. Here it is larger. Here it is actually designed in 60 nanometer, I guess. And on-chip, off-chip memory are very much comparable. So you can see this TPU version 3 is very similar to Volta, at least in terms of some of the metrics. Here MHC per core is small. And it is 2. Here it is 8. Cores per chip, it is 2. Here it is 80. So these are differences. And you can study this link for more information.